You are living in the most extraordinary moment in cosmic history. Right now, as you're listening to these words, you exist during what future astronomers will look back on as the golden age of the universe. The age when stars filled the cosmos with light, when galaxies shone brilliantly against the darkness, when the evidence of the Big Bang was still visible in the sky, when the universe was neither too young and chaotic to support life, nor too old and dispersed to be interesting. You're here during the sweet spot, the brief window, cosmically speaking, when the universe is full of light and possibility and observable structure. And most people have no idea how special this timing is. They don't realize that we're witnessing something that won't last forever, that future beings, if they exist trillions of years from now, will look up at a very different sky, a darker sky, an emptier sky, a sky that doesn't reveal the universe's history the way ours does. They'll envy us. They'll wish they could have seen what we can see, because we're living during the universe's golden era, and golden eras don't last. Tonight, I want to take you on a journey through cosmic time. I want to show you why the moment we're living in right now is so special. Why the universe's current age, 13.8 billion years after the Big Bang, represents a peak, an optimum, a time when more is possible, more is visible, more can be understood than at almost any other point in the past or future. And I want you to understand what this means for us, for our existence, for our ability to comprehend the cosmos, for the privilege and responsibility that comes with living during this extraordinary era. Because when you grasp the timing, when you see where we fit in the vast sweep of cosmic history, it changes everything. It makes you appreciate the light while we have it, makes you realize that the stars won't shine forever, makes you understand that we're witnessing something precious and temporary. Let me start by asking you a question. What makes a time period golden? In human history, we talk about golden ages. The golden age of Athens, when philosophy and democracy flourished. The Islamic golden age, when science and mathematics advanced dramatically. The Italian Renaissance, when art and human achievement reached new heights. These weren't just prosperous times. They were moments when conditions aligned perfectly to allow something special to happen. When the right resources, the right ideas, the right people came together in the right place at the right time. Golden ages are rare. They're temporary. They require specific conditions that don't last forever. Athens fell. The Islamic Golden Age declined. The Renaissance ended. But while they lasted, extraordinary things happened. Things that shaped human civilization for centuries to come. The universe has its own golden ages, periods when conditions are optimal for certain things to occur. And we're living in one right now. The stelliferous era, the age of stars. But before I explain why this is golden, before I show you what makes our cosmic moment so special, you need to understand the bigger picture. You need to see the full timeline of cosmic history, because the universe hasn't always been the way it is now, and it won't always be this way in the future. The universe has phases, eras, each one characterized by different conditions, different dominant processes, different possibilities. Cosmologists have divided the universe's past and future into several distinct eras. The primordial era, the first few minutes after the Big Bang, when the universe was too hot and dense for even atoms to exist. Just a soup of elementary particles in extreme conditions. The stelliferous era, the age of stars, which began a few 100 million years after the Big Bang and will continue for trillions of years. That's the era we're in now, the degenerate era which will follow after all the stars have burned out, when the universe will be dominated by stellar remnants like white dwarfs and neutron stars slowly cooling in the darkness. The black hole era, when even those remnants will have decayed or been consumed, and black holes will be the last remaining massive objects in an otherwise empty universe. And finally, the dark era, when even the black holes have evaporated through Hawking radiation, leaving nothing but a thin soup of particles spread across an incomprehensibly vast and cold universe, approaching maximum entropy. We're in the stelliferous era, the age of stars, and not just anywhere in this era, but at a particularly interesting moment within it. To understand why, you need to understand what the stelliferous era actually is and how it began. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before this moment called recombination, the universe was a hot plasma, opaque to light. Photons couldn't travel far before being scattered by free electrons. But when atoms formed, the universe suddenly became transparent. Light could travel freely for the first time. The cosmic microwave background radiation we observe today, that faint glow coming from every direction in space, is light from this moment. Light that's been traveling for 13.8 billion years, stretched by the expansion of space from visible and infrared wavelengths into microwaves. But the universe was still dark. There were no stars yet, no galaxies, just hydrogen and helium gas slowly collapsing under gravity into denser and denser clouds. The first few 100 million years after the Big Bang are called the Cosmic Dark Ages. No stars, no light, just darkness and gradually forming structure. Then, somewhere between 100 and 400 million years after the Big Bang, the first stars formed. Massive stars, much larger than the Sun, made almost entirely of hydrogen and helium. Because those were the only elements that existed, these first stars, called population 3 stars, burned hot and died young. Within a few million years, they exploded as supernovae, scattering heavier elements into space. Carbon, oxygen, iron, all the elements needed for planets and eventually life. The darkness was ending. The stelliferous era was beginning. And over the next few 100 million years, star formation accelerated. Galaxies formed, clusters of galaxies. The cosmic web of structure began to take shape. The universe filled with light, billions and billions of stars burning bright against the cosmic darkness. This is the era we're still in, the age of stars, the age of light. But here's what most people don't realize. The stelliferous era, while it will last for trillions of years total, has already peaked in some crucial ways. Star formation, the rate at which new stars are born, peaked about 10 billion years ago. 3.8 billion years ago, when the Sun and Earth formed, the universe had already passed its prime in terms of star production. It was already on the declining slope. Fewer new stars were being born each year compared to the peak billions of years earlier. The universe was, in a sense, already beginning its long, slow decline into darkness. So, why do I say we're living in a golden era if we're already past the peak? Because peak isn't the same as optimal. Let me explain what I mean. Yes, the universe was making more stars 10 billion years ago than it is now. But 10 billion years ago, the universe was more chaotic, more violent. Galaxies were colliding more frequently. Supernovae were more common. The radiation environment was harsher. And crucially, there hadn't been enough time yet for the full diversity of planetary systems to develop, for chemistry to become complex, for conditions to stabilize in ways that might allow life to emerge. The early universe was like early childhood, full of energy and growth, but chaotic and undeveloped. Now, 13.8 billion years after the Big Bang, we're in something like the universe's prime. Not its youth, but its maturity. The chaos has settled. Galaxies have formed stable structures. Stars have gone through multiple generations, creating and distributing heavy elements. Planetary systems have had time to form around stable stars. Chemistry has become rich and complex, and crucially, from an observational standpoint, we're at a moment when we can see an enormous amount about the universe's history and structure. The cosmic microwave background is still detectable, still bright enough that our telescopes can observe it, map it, learn from it. Future civilizations, trillions of years from now, won't have this. The expansion of the universe will have red-shifted this radiation into invisibility. Galaxies are still relatively close together. We can observe billions of them. We can see the large-scale structure of the universe, the cosmic web, the distribution of matter across enormous distances. Future civilizations, after the accelerating expansion has had trillions of years to work, will live in isolated galaxy clusters separated by voids so vast that they'll never see other galaxies. They won't know about the cosmic web. They won't be able to map large-scale structure. Star formation is still happening. The universe is still making new stars, even if at a reduced rate compared to the peak. We can observe stellar nurseries, watch stars being born, study the processes that create new suns. Future civilizations, after all. The available gas has been consumed or dispersed, will live in a universe where star formation has completely ceased. They'll never see a star being born. These conditions, this combination of factors, they define our cosmic moment. We're past the chaotic youth, but still billions of years before the lonely old age. We're in the sweet spot, the golden era, when the universe is both interesting and comprehensible, full of light and structure and observable phenomena. Let me give you a specific example to make this concrete. The cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space. Right now, in our time, it's about 2.7 Kelvin, just a few degrees above absolute zero. Cold, but still detectable with sensitive instruments. We've built satellites specifically to observe it. The Planck mission mapped temperature fluctuations across the sky with exquisite precision. Those fluctuations, tiny variations in temperature on the order of a few millionths of a degree, tell us about the state of the universe 380,000 years after the Big Bang. They reveal how matter was distributed, where the seeds of galaxies were planted, how the universe evolved from near uniformity to the rich structure we see today. This is incredibly valuable information. The cosmic microwave background is our direct window into the early universe, our way of observing conditions billions of years ago. Without it, we'd have to rely entirely on theory and indirect evidence to understand the Big Bang and its immediate aftermath. But the cosmic microwave background is cooling. As the universe expands, the wavelength of this radiation stretches, redshifts, gets longer, and as the wavelength gets longer, the temperature drops. It's been cooling for the entire history of the universe. When the cosmic microwave background first formed, it was about 3000 Kelvin, hot enough to glow orange like an incandescent light bulb. As the universe expanded, it cooled to thousands of Kelvin, then hundreds, then tens, and now it's down to 2.7 Kelvin. And it will keep cooling. In another 100 billion years, it will be about 0.3 Kelvin, 10 times colder than now, still technically detectable but much harder to observe. Background noise from other sources becomes relatively more significant. In a trillion years, it will be about 0.03 Kelvin, buried in noise, practically unobservable, and eventually, after enough time, it will cool to the point where it's completely indistinguishable from the quantum fluctuations of the vacuum, effectively gone. Future civilizations living trillions of years from now won't be able to see the cosmic microwave background. They won't have direct evidence of the Big Bang. They'll have to infer it from other observations, from the expansion of the universe, from the abundances of light elements, from theoretical models. But they won't be able to see the afterglow the way we can. They'll read about it in whatever records survive from our era. They'll see our maps, our measurements, our analysis, and they'll wish they could have observed it directly, wish they could have seen what we can see. We have that privilege. We can observe the cosmic microwave background. We can map its fluctuations. We can learn directly about the early universe from light that's been traveling for 13.8 billion years. That's a gift, a temporary gift, cosmically speaking, but we're here to receive it. This is just one example, but it illustrates the broader point. We live at a time when the universe is still revealing its secrets, still showing us its history, still full of observable phenomena that won't last forever. Now let me tell you about another aspect of our golden era, the visibility of galaxies and large-scale structure. Right now, we can observe billions of galaxies. We've photographed them, catalogued them, measured their distances and properties. We can see how galaxies are distributed across space, how they cluster together into groups and clusters, how those clusters connect via filaments of dark matter and gas, forming the cosmic web. This structure, this pattern of matter distribution, it reveals how the universe evolved, how tiny fluctuations in the early universe grew through gravity into the large-scale structure we see today. It tests our theories of cosmology, confirms predictions about dark matter and dark energy, shows us how the universe has changed over billions of years. But this visibility won't last. The universe is expanding. And not just expanding, but accelerating. The expansion rate is increasing over time, driven by dark energy. This acceleration means that distant galaxies are receding faster and faster. Their light is being red-shifted more and more, and eventually they'll recede so fast that their light can never reach us. They'll disappear beyond the cosmic horizon. In about 100 billion years, all galaxies outside our local group will have receded beyond the horizon. They'll be gone, invisible. No amount of telescope power will bring them back because their light simply won't be able to reach us anymore. The space between us and them will be expanding faster than light can cross it. A civilization living in the Milky Way 100 billion years from now will look out and see only the local group. Our galaxy and Andromeda merged into one by then, and maybe a few small dwarf galaxies. That's it. The rest of the universe will be dark, empty, gone. They won't see the cosmic web, won't be able to map large-scale structure, won't be able to study billions of galaxies the way we can. They'll look at our records, our observations, our catalogs. They'll see that we documented billions of galaxies. They'll read our measurements of cosmic structure, and they'll realize that we lived during a special time, a time when the universe was still visible, still observable across vast distances, when you could point a telescope at the sky and see the full richness of cosmic structure. We have that now. We can see galaxies billions of light years away. We can observe the large-scale distribution of matter. We can watch how structure has evolved over cosmic time by looking at galaxies at different distances, seeing them as they were at different epochs in the past. This observational wealth, this ability to see so much of the universe, it's temporary. It's a feature of our particular cosmic moment, and it's one of the things that makes this era golden. Then there's star formation itself. I mentioned earlier that the rate of star formation peaked about 10 billion years ago. Since then, it's been declining. The universe is using up its gas. The raw material that makes stars is being consumed, locked up in existing stars, blown out of galaxies by supernovae and black hole winds, diluted by the expansion of space. The star formation rate today is about 3% of what it was at the peak. 3%. The universe is making new stars 30 times slower than it did 10 billion years ago. And this decline will continue. In another few trillion years, star formation will have essentially stopped. The last stars will be born. After that, no more. The existing stars will burn their fuel and die. Red giants will shed their outer layers. Supernovae will explode. White dwarfs will cool. Neutron stars will spin down. Black holes will lurk silently in the darkness. But no new stars will form to replace them. The universe will slowly dim as existing stars exhaust their fuel and wink out one by one. This transition from light to darkness will take a long time. The smallest stars, red dwarfs, can burn for trillions of years. Long after stars like the Sun have died, red dwarfs will still be fusing hydrogen in their cores, providing light and heat to whatever remains of the cosmos. But eventually, even they'll run out of fuel, even they'll die. And when the last star finally exhausts its hydrogen and fades to a cooling ember, the stelliferous era will be over. The age of starlight will end. The degenerate era will begin. A time of darkness, a time of stellar corpses cooling in the void. A time when the universe will be unrecognizably different from what we see now. But that's trillions of years in the future. Right now, stars are still being born. The rate is declining, yes, but it's not zero. We can still observe stellar nurseries, still watch the process of star formation, still see new suns igniting in clouds of gas and dust. Future civilizations, living after star formation has ceased, won't have this. They'll study the stars that exist, analyze their properties, understand the physics of fusion and stellar evolution. But they'll never see a star being born. They'll never observe the process directly. That's another privilege of our era, another aspect of why this moment is golden. We're witnessing active creation. The universe is still making new stars, new planetary systems, new opportunities for complexity and perhaps life. We're not just observers of a static, frozen cosmos. We're watching it evolve, watching it create, and that's special. Now, let me connect this to life, to the possibility of beings like us existing and contemplating the cosmos. Because the timing of our existence isn't random. We couldn't have existed much earlier. And if we'd come much later, conditions might have been less favorable. Life as we know it requires heavy elements: carbon, oxygen, nitrogen, phosphorus, iron, all the elements beyond hydrogen and helium. These elements weren't present when the universe began. They had to be created through nucleosynthesis in stars and supernovae. The first stars were made almost entirely of hydrogen and helium. They couldn't have hosted rocky planets. There was no carbon for organic chemistry, no oxygen for water, no iron for planetary cores. The universe needed multiple generations of stars, needed massive stars to live short lives and die in spectacular explosions, scattering heavy elements into space, needed those enriched clouds to collapse and form new stars with planetary disks rich in heavy elements. This process takes time, billions of years. The Sun is a third-generation star, maybe fourth. It formed from a molecular cloud that had been enriched by countless previous generations of stars. That's why the Earth exists, why rocky planets exist in our solar system, why life could emerge. The necessary raw materials, the heavy elements, they weren't available in the early universe. So life as we know it couldn't have started much before about 8 or 9 billion years after the Big Bang. Before that, there simply weren't enough heavy elements around. The universe needed time to cook up the chemistry required for complex structures. But there's also a limit on the other end. If you wait too long, conditions become less favorable. As star formation declines, as gas is consumed or dispersed, as the universe continues to expand and cool, opportunities for new planetary systems decrease. Fewer stars means fewer planets. Declining star formation means fewer chances for life to emerge. And beyond just the raw numbers, there's the question of stability. Life needs stable conditions. a star that burns steadily for billions of years, a planet in the habitable zone, protection from excessive radiation. These conditions are most likely during the mature phase of a star's life, when it's burning hydrogen stably on the main sequence. Too early in the universe, when things were more chaotic and violent, stability was harder to come by. Too late, when star formation has ceased and existing stars are aging, opportunities decline. So there's a window, a habitable epoch of the universe, a time when conditions are most favorable for life, and we're in it. We're in the sweet spot between too early, when heavy elements were scarce, and too late, when opportunities have declined. Our sun formed 4.6 billion years ago, about 9 billion years after the Big Bang. It's a stable star, burning hydrogen steadily, providing consistent energy to Earth. It will continue doing so for another 5 billion years or so before beginning to evolve into a red giant. This is ideal timing. The universe had enough time to create the heavy elements we need. Enough time for galaxies to settle into stable structures. Enough time for multiple generations of star formation to enrich the cosmos with the chemistry of life. But not so much time that opportunities have passed. Not so late that star formation has ceased, or that the universe has expanded so much that everything is isolated and dispersed. We're here at the right time, and that's not coincidence. It's the result of the cosmic timeline, the sequence of events that had to happen for complex life to emerge. But it's also temporary, a window that won't stay open forever. Future life, if it emerges billions or trillions of years from now, will face a different universe, one with fewer stars, less ongoing creation, a dimmer, emptier cosmos. They might still exist. Life is resilient and creative, but their universe will be less vibrant, less full of light and possibility. They'll look back at eras like ours and recognize that we lived during a special time, the peak of the stelliferous era, when stars filled the cosmos, when galaxies were visible across vast distances, when the cosmic microwave background was still detectable, when the universe was mature enough to be interesting but young enough to still be active and observable. That's the golden era, and we're living in it right now. Let me paint you a picture of what we can see that other eras couldn't. Imagine you're an astronomer in the very early universe, say 1 billion years after the Big Bang. You'd see a cosmos very different from ours. Galaxies would be smaller, less well-formed. Many would still be in the process of merging and growing. Star formation would be intense. The universe would be bright in some ways, but chaotic. The cosmic microwave background would still be relatively warm, maybe 30 Kelvin instead of 3. It would glow in the far infrared, flooding the sky with background radiation that would interfere with observations. You wouldn't be able to see as far or as clearly because the universe would be smaller, denser, more opaque in certain wavelengths. And, crucially, if you tried to look back in time by observing distant objects, you wouldn't be able to see as far back. The universe would only be 1 billion years old. The most distant thing you could observe would be from a few 100 million years after the Big Bang at most. You couldn't see the cosmic dark ages, couldn't see the era before the first stars formed. your view of cosmic history would be truncated. Now imagine you're an astronomer in the far future, say 100 trillion years from now. The last stars are dying. The universe is mostly dark. The cosmic microwave background has cooled to near absolute zero, effectively undetectable. All galaxies outside your local group disappeared beyond the cosmic horizon trillions of years ago. Your sky contains maybe one galaxy, possibly merged from several older ones. That's all you can see, all you'll ever see. Star formation ended trillions of years ago. You've never seen a stellar nursery, never watched a star being born. The stars that exist are old. Red dwarfs burning slowly, white dwarfs cooling, neutron stars spinning silently. No hot young stars, no supernovae, no active galactic nuclei. The universe is quiet, dark, sparse. You can study the stars you have, understand their physics, but you're missing so much. You can't see the cosmic microwave background, can't directly observe evidence of the Big Bang. You can't see other galaxies, can't study large-scale structure, can't watch star formation. Your view of the universe is limited, impoverished. If you find ancient records from civilizations that lived during the Stelliferous era, during our time, you'll read about things you can't see. Billions of galaxies. The cosmic web, the afterglow of the Big Bang. Active star formation. You'll realize that you missed it, that you came too late, that the golden age ended before you arrived. But you, right now, don't have these limitations. You're between these extremes. The universe is old enough to be interesting, to have developed complex structure, to have created the conditions for life, but it's young enough that the lights are still on. The evidence is still visible. The cosmos is still observable. You can see the cosmic microwave background, can map its fluctuations, can learn about the early universe directly. You can observe billions of galaxies, can study their distribution, can watch how structure evolved over cosmic time. You can see stars being born in nebulae like the Orion Nebula, can watch stellar nurseries in action, can study the full life cycle of stars from birth to death. You can observe supernovae exploding, can watch as massive stars die and scatter heavy elements into space, can see the recycling process that enriches the universe. You have access to all of this, all these windows into cosmic processes and history. This is the golden era. This is why our moment in cosmic time is so special. We're not too early, not too late. We're just right. The universe has given us a gift, a window of time when it's fully observable, when its history is written in the sky, when light fills space and reveals structure across billions of light years. But this gift is temporary. Cosmically speaking, it won't last. The universe is evolving, changing, moving toward a future that will be darker and emptier and less observable. We're catching the universe during its prime, and that's extraordinary. That's something to appreciate, something to marvel at. You're alive during the age of starlight, during the era when the cosmos shines bright, when you can look up on a clear night and see stars scattered across the darkness, when telescopes can observe galaxies billions of light years away, when the evidence of the universe's beginning is still visible in the sky. This is the golden era, and you're here for it. You get to witness it. You get to be part of a species that's conscious during this extraordinary cosmic moment, that can look up and understand what we're seeing, that can contemplate our place in the vast sweep of cosmic time. That privilege, that opportunity, it's what makes this era golden. Not just the physics of stars and galaxies, but the fact that we're here to observe it, to understand it, to appreciate it. The universe is 13.8 billion years old. It will exist for trillions of years more, and you exist during the brief window when it's most observable, most full of light, most interesting. That's not random. That's the result of the cosmic timeline requiring billions of years to create the conditions for life. But it's also temporary, a phase that will pass, and that makes it precious, makes it something to cherish, makes it something worth protecting and preserving and understanding as fully as we can, because we're the ones who can see it. We're the witnesses to the golden age of Starlight. And what we observe, what we learn, what we document, that's our gift to the future. To civilizations that might come after, when the universe is darker and emptier. They'll look at our records, our observations, our measurements, and they'll see what we saw. They'll understand what the universe looked like during its prime, during the age when stars filled the cosmos with light. They'll know about the golden era because we're here to document it. That's our cosmic responsibility, our privilege and our duty, to observe, to learn, to preserve what we discover, because we're living during a time that won't come again. The universe's golden age, the age of Starlight, and we're just beginning to understand how special this moment really is. Let me help you understand this even more deeply by walking through what makes our specific moment so remarkable from an observational standpoint. Because it's one thing to know abstractly that we live in a golden era. It's another to really grasp what that means in concrete terms. What we can see that past and future can't. Start with something specific. The Hubble Deep Field. In 1995, astronomers did something that seemed crazy at the time. They pointed the Hubble Space Telescope at a tiny patch of seemingly empty sky, an area about the size of a grain of sand held at arm's length. There were no bright stars visible in this region, no obvious galaxies, just darkness. And they exposed the image for 10 days. 10 days of Hubble's precious observation time pointed at apparent nothingness. The result was revolutionary. In that tiny patch of sky, Hubble detected about 3,000 galaxies, 3,000 island universes, each containing billions of stars, in an area that looked empty to previous observations. And these weren't nearby galaxies. Many of them were incredibly distant, so far away that we're seeing them as they were billions of years ago when the universe was young. The Hubble Deep Field, and later the Ultra Deep Field, showed us that the universe is densely packed with galaxies, that even in the darkest, emptiest-looking regions of sky, there are thousands of galaxies if you look deep enough. That revelation, that ability to see so far and so deep, that's a privilege of our era. The galaxies in the deep field are still visible, still observable. Their light, which has been traveling for billions of years, is still reaching us. The expansion of the universe hasn't yet carried them beyond our observational horizon. But wait long enough. let the accelerating expansion continue for another 100 billion years or so, and many of those galaxies will be gone, receded beyond reach. No telescope, no matter how powerful, will be able to see them because their light will never catch up to us through the expanding space. Future astronomers will look at our Hubble Deep Field images and see galaxies that they can no longer observe. They'll read our measurements, our distance estimates, our analysis of what those distant galaxies looked like billions of years ago. And they'll realize that we had something they've lost, a view into the deep universe that's no longer available. That's what I mean by the golden era. We can see things that won't always be visible. We have access to information about the universe that's temporary. And, crucially, we're using that access. We're building telescopes, making observations, creating catalogs, documenting what we see. We're being good stewards of our cosmic moment. Consider another example. The large-scale structure of the universe, the cosmic web. Right now, we can map how galaxies are distributed across enormous volumes of space. Surveys like the Sloan Digital Sky Survey have catalogued millions of galaxies, measured their distances, mapped their three-dimensional positions. And what we see is remarkable. Galaxies aren't randomly distributed. They cluster together along filaments, forming a web-like structure. These filaments connect galaxy clusters with vast voids between them where few galaxies exist. This structure, this cosmic web, it's the result of billions of years of gravitational evolution. Tiny density fluctuations in the early universe grew over time as gravity amplified them. Denser regions attracted more matter, becoming denser still. Galaxies formed where the density was highest. And the overall pattern reflects the initial conditions of the universe, the distribution of matter in the first moments after the Big Bang. By mapping this structure, we're learning about cosmic history, about how the universe evolved from nearly uniform to highly structured, about the role of dark matter in shaping galaxy distributions, about how dark energy affects the growth of structure over time. But this mapping, this ability to see large-scale structure, it requires being able to observe many galaxies across vast volumes. And that's only possible because those galaxies are still visible, still close enough that their light reaches us. Wait another 100 billion years, and the cosmic web will be invisible. The accelerating expansion will have carried most galaxies beyond the horizon. Future astronomers will see only their local galaxy cluster. They won't be able to map large-scale structure because they won't be able to see it. They'll have our maps, our catalogs, our observations, but they won't be able to verify them, won't be able to extend them, won't be able to discover new aspects of large-scale structure because the evidence will have expanded beyond their reach. Again, we have something temporary, something precious, a view of cosmic structure that won't last forever. Now, think about the cosmic microwave background in more detail. I mentioned it earlier, but let me really drive home why this is so important and why future civilizations will envy us for being able to see it. The cosmic microwave background is not just any radiation. It's a snapshot of the universe as it was 380,000 years after the Big Bang. Before this moment, the universe was opaque, too hot and dense for light to travel freely. But When atoms formed and the universe became transparent, all the light that had been trapped in the hot plasma suddenly could travel. And that light, stretched by billions of years of cosmic expansion, is what we see today as the cosmic microwave background. What makes it so valuable is the information it contains. The temperature fluctuations across the sky, those tiny variations on the order of millionths of a degree. They encode information about the early universe, about the distribution of matter and energy, about the density of different components like ordinary matter, dark matter, and dark energy, about the geometry of space itself. By measuring these fluctuations precisely, which we've done with satellites like Kobe, WMAP, and Planck, we can determine fundamental cosmological parameters. How old is the universe? What's its composition? How fast is it expanding? What's the density of dark matter? All of this from studying the cosmic microwave background. It's our most direct window into the early universe, our way of seeing conditions just a few 100,000 years after the Big Bang, before stars formed, before galaxies existed, when the universe was just a hot, dense, nearly uniform gas, slowly cooling and expanding. But, as I mentioned, the cosmic microwave background is cooling. As the universe expands, the wavelength of this radiation stretches. The temperature drops. Right now, it's 2.7 Kelvin. In 100 billion years, it will be 10 times colder. In 1 trillion years, 100 times colder. And the colder it gets, the harder it is to detect. Eventually, it becomes indistinguishable from the background noise of the universe. The quantum fluctuations of the vacuum, the thermal radiation from any remaining matter, it effectively disappears. Future astronomers living trillions of years from now won't be able to see the cosmic microwave background. They'll lose this window into the early universe. They'll have to rely on theory and indirect evidence to understand the Big Bang, but they won't have the direct observational confirmation that we have. They won't be able to measure the fluctuations, won't be able to see the snapshot of the universe at 380,000 years. That information will be gone unless we preserve it. Unless we document what we're observing now, unless we create records that survive into the far future so that future civilizations can know what the cosmic microwave background looked like when it was still observable. That's part of our responsibility, part of what makes this golden era not just a privilege, but a duty. We're the ones who can see these things. We're the witnesses. And what we observe and record will be the only evidence future eras have that these phenomena ever existed. Let me give you one more example. Supernovae. These spectacular explosions happen when massive stars reach the end of their lives. The core collapses. The outer layers are blown off in an explosion that, for a few weeks, can outshine an entire galaxy. We observe supernovae regularly, several per year in nearby galaxies, many more in distant galaxies if we survey large areas of sky. These explosions are important for multiple reasons. They create and distribute heavy elements. They provide energy to the interstellar medium, and they serve as distance indicators, helping us measure cosmic expansion. But supernovae require stars. Specifically, they require massive stars to exist and reach the end of their lives. And massive stars require ongoing star formation because they don't live very long. A star 10 times the mass of the Sun lives for only about 20 million years before going supernova. In the far future, when star formation has ceased, when the last massive stars have already died, supernovae will become increasingly rare. Eventually, they'll stop altogether. No more massive stars means no more core collapse supernovae. Future astronomers will study the remnants of ancient supernovae. They'll understand the physics, but they'll never see one happen, never observe the light curve, never watch the explosion evolve over weeks and months. That's another aspect of our golden era. We're living during a time when the universe is still active, still dynamic, still producing spectacular phenomena like supernovae. We can observe these events, study them, learn from them. Future eras will have to rely on our observations, our data, our understanding, because the universe will have settled into a quieter state, less active, less dramatic, more static. Now, I want to address something you might be thinking. You might be wondering, if this is such a golden era, if we're so privileged to live at this time, doesn't that seem suspicious? Doesn't it seem like too much of a coincidence that we happen to exist right at this special moment? This is actually a profound question, and it relates to something called the anthropic principle. The idea that our observations of the universe are necessarily biased by the conditions required for observers to exist. We can only observe the universe during times and places where conditions allow complex life to emerge. We couldn't exist during the first few 100 million years after the Big Bang because there weren't heavy elements yet. We couldn't exist trillions of years in the future when star formation has ceased and existing stars have mostly died out. We need specific conditions: a stable star, a rocky planet with the right chemistry, enough time for evolution to produce complex life. These conditions aren't available at all times in cosmic history. They're available during a window, a habitable epoch. And, naturally, we find ourselves living during that window because we couldn't exist outside it. So, yes, we live during a special time, but it's not a coincidence. It's a necessity. If conscious observers exist, they must exist during times when the conditions support their existence. And those times happen to coincide with what we'd call a golden era for other reasons too. The universe is mature enough to have interesting structure, young enough to still be active and observable, full of stars and planets and chemical complexity. This is when observers can exist, and therefore this is when observers do exist. But that doesn't diminish the specialness. It doesn't make our moment any less remarkable. Yes, we couldn't exist at other times, but we do exist now. And now happens to be an extraordinary period in cosmic history. A brief window, relatively speaking, when the universe is full of light and observable structure, when conditions are optimal for both life and scientific observation. That's still special, still something to appreciate, even if it's not a coincidence that we're here to appreciate it. Think about it another way. The stelliferous era will last for perhaps 100 trillion years total. Star formation began about few 100 million years after the Big Bang, and will continue for trillions of years into the future. But the golden age within that era, the time when conditions are truly optimal, when the most information is accessible, when the universe is most observable, that's a much shorter period. Maybe a few 100 billion years, maybe less, depending on how you define it. We're 13.8 billion years into the era, past the peak of star formation, but still in a period of relative abundance. The cosmic microwave background is still visible. Galaxies are still observable across vast distances. Large-scale structure is developed but not yet dispersed beyond visibility. We're in the sweet spot. And that sweet spot, that optimal period, it's a small fraction of the total stelliferous era. Even granted that we must exist during the stelliferous era for life to be possible, we're fortunate to exist during this particular phase of it. A bit earlier, and the universe would have been more chaotic, less developed, possibly less conducive to stable planetary systems and long-term evolution. A bit later, and while life might still be possible, the observational opportunities would be declining. The universe would be dimmer, emptier, less information-rich. So, even within the constraints of when life is possible, we've hit a particularly good moment. A golden age within the age of Starlight. That's worth reflecting on, worth appreciating, because it's temporary. The universe is evolving, changing, moving inexorably toward a future that will be different from the present, darker, quieter, less observable. We're catching the universe during its prime, and that makes our moment in cosmic time genuinely special, not just for us, but objectively, in terms of what can be observed and understood about the cosmos. If you could choose when to exist, when to be alive and conscious and capable of studying the universe, this would be a good choice. Maybe not the absolute peak of star formation 10 billion years ago, but close to it. Late enough that the universe has matured, early enough that it's still vibrant and full of light. You made a good choice, or rather, the universe made a good choice in when to create conditions suitable for you to exist. This is your cosmic moment, the golden age, and understanding that, really grasping what it means to live during this extraordinary time, it should change how you see everything, how you think about the stars, how you consider your place in the universe, how you appreciate the privilege of consciousness during the age of Starlight. Let me make this even more concrete by talking about what you can see with your own eyes. Because the golden era isn't just about telescopes and satellites and scientific observations. It's about what's visible in the night sky, what you can experience directly. Go outside on a clear, dark night, away from city lights if possible. Look up. What do you see? Stars, hundreds or thousands on them, depending on how dark your sky is. Some bright, some dim. Different colors if you look carefully. White, blue-white, yellow, orange, red. Each one a sun like ours. Some smaller, some larger, some younger, some older. All of them burning hydrogen, fusing it into helium, converting mass into energy, shining across the light years. That sight, that sky full of stars, it's what the golden era looks like. It's what the age of Starlight means. Those points of light filling the darkness. Each one representing a fusion reactor a massive ball of plasma held together by gravity, generating energy that streams out into space. Some of that energy reaches your eyes. Photons that left those distant suns years or centuries ago traveled across the void, entered Earth's atmosphere, and struck your retina, triggering electrical signals that your brain interprets as light. You're connected to those stars. You're seeing them directly, experiencing the age of starlight firsthand. And on a really dark night, away from light pollution, you can see something even more spectacular. The Milky Way, that band of pale light stretching across the sky. It looks like a cloud or a river of light. Ancient peoples told stories about it. The Greeks thought it was milk spilled by the goddess Hera. The Chinese saw it as a river separating lovers. Various cultures saw different things, but they all recognized that this band of light was special, different from the individual stars. What you're seeing when you look at the Milky Way is our galaxy. You're inside it, looking at it from within. All those individual stars you can pick out, they're relatively nearby, within a few hundred or few thousand light years. But the Milky Way, that glowing band, that's the combined light of billions of stars too far away and too faint to see individually. They blend together into a continuous glow. You're seeing across tens of thousands of light years, seeing the disk of our galaxy edge on, seeing the collective light of billions of distant suns. That's extraordinary. That's a direct, visceral experience of the golden era. You're not just reading about stars or looking at images from telescopes. You're seeing them yourself, with your own eyes, experiencing the age of starlight personally. But this won't last forever. Not for humanity, certainly. The sun will eventually evolve into a red giant, making Earth uninhabitable. We'll have to leave if we want to survive as a species. And wherever we go, we'll see different stars, different constellations, a different night sky. The familiar patterns will be gone, replaced by new arrangements. But even more profoundly, the stars themselves won't last forever. The age of starlight, the stelliferous era, it will end. Trillions of years from now, the last star will burn out. The last fusion reactor will exhaust its fuel. The cosmos will go dark. And any beings alive in that distant future, assuming life persists that long, will never see a sky full of stars. They'll look up at darkness. Maybe they'll see the faint glow of cooling stellar remnants, white dwarfs radiating their stored heat, brown dwarfs that never quite ignited, but nothing like the brilliant star-filled sky we can see now. They'll read about it in whatever records survive from earlier eras. They'll see our photographs, our observations, our descriptions of what the night sky looked like during the age of starlight. And they'll envy us. They'll wish they could see what we can see, experience what we can experience, stand under a sky blazing with stars. That's what makes this golden. That's what makes this time special. The stars are shining. The universe is full of light. And we're here to see it, to experience it, to appreciate it, before it fades. Now I want you to think about time, not in the human sense, not days or years or even centuries, but in the cosmic sense. The universe is 13.8 billion years old. That's the span from the Big Bang to now, 13.8 billion years. If you compress that entire history into a single year, with the Big Bang happening at midnight on January 1st, human civilization wouldn't appear until the last few seconds of December 31st. All of recorded history, from the first written records to today, would be less than a second in this cosmic calendar. Our entire species has existed for only the briefest moment. We're newcomers, late arrivals to a universe that's been evolving for billions of years before we appeared. But here's what's important. We arrived at a good time. The universe is 13.8 billion years old enough to have created heavy elements through multiple generations of stars, old enough to have developed complex structure, old enough to have formed stable galaxies with stable stars, capable of hosting stable planetary systems where complex chemistry can unfold over billions of years. But it's not too old. Star formation is still ongoing. The cosmic microwave background is still visible. Galaxies haven't dispersed beyond observability. The universe is still active, still interesting, still full of light and structure. If humans had somehow appeared earlier, say just a few billion years after the Big Bang, we'd be living in a less mature universe, fewer heavy elements, more chaotic conditions, possibly less stable environments for life to develop. If we appeared much later, say hundreds of billions of years from now, we'd be living in a darker universe, lower star formation, fewer bright stars, less observable structure. The golden age would have passed, but we appeared now, 13.8 billion years after the beginning, at a time when the universe is mature enough to be interesting, but young enough to still be vibrant. That timing, that's part of what makes this the golden era. We're not just observers, we're well-timed observers. We showed up at a moment when there's much to see and the tools to see it. The universe is revealing its secrets during our watch, and we're learning to read them, building telescopes, conducting observations, developing theories, piecing together the cosmic story. We're living during a time when this is possible, when the evidence is available, when the universe is observable. That won't always be true. The evidence will fade, the observability will decline, the universe will become harder to study as it ages and disperses. But for now, for our time, it's an open book, and we're learning to read it. That's the privilege of the golden era. Not just that the universe is special during our time, but that we're here to appreciate it, to study it, to understand it, to document what we observe so that knowledge persists into eras when direct observation will be more limited. This is our moment, our cosmic responsibility, our gift and our duty, to see what can be seen, to learn what can be learned, to preserve what we discover, because we're the witnesses to the golden age, the age of starlight, the time when the universe shines brightest and reveals most about its nature and history. And what we do with this opportunity, how we use this privilege, that matters. That's part of what defines our time in the cosmic timeline. We're not just passive observers, we're active participants in the universe's ongoing story. We're the part of the cosmos that's woken up and become aware. That's looking around and trying to understand what we're part of. And we're doing this during a time when understanding is possible, when the evidence is abundant, when the universe is cooperating with our efforts to comprehend it. That's special. That's meaningful. That's what makes this the golden era. And it's happening now, during your lifetime. During this moment in cosmic history, you're part of it. You're living through it. You're witnessing the age of Starlight. And hopefully, after everything we've explored together, you understand why that's so extraordinary, why this time is so precious, why we're fortunate to exist when we do. The stars are shining, the universe is observable, and we're here to see it all. That's the golden era, and we're living in it right now. Let me take you deeper into what makes stars so central to this golden era. Because stars aren't just beautiful lights in the sky. They're not just interesting astronomical objects. They're the engines that make everything possible, the factories that create the elements, the power sources that enable life. Without stars, the universe would be a very different place, a much darker, much emptier, much less interesting place. And our era, the stelliferous era, is defined by their abundance and activity. Think about what a star actually does. At its core, it's fusing hydrogen into helium, taking 4 hydrogen nuclei and combining them into one helium nucleus. This process releases energy because the helium nucleus weighs slightly less than the 4 hydrogen nuclei you started with. That missing mass, that tiny fraction of a percent, gets converted into energy according to Einstein's famous equation, E equals mc squared. And because the speed of light squared is such an enormous number, even a tiny amount of mass converts into a tremendous amount of energy. The Sun, our star, converts about 4 million tons of mass into energy every single second. 4 million tons every second. That's incomprehensible in human terms, but it's what powers the Sun, what makes it shine, what provides the light and heat that makes life on Earth possible. And the Sun is just one star among hundreds of billions in our galaxy, trillions in the observable universe, each one a fusion reactor, each one converting mass into energy, each one shining. This is what the golden era looks like at a fundamental level, the universe filled with fusion reactors, powered by nuclear processes that convert hydrogen into heavier elements and release energy in the process. But stars do more than just produce light and heat. They create elements. When the universe began, it was almost entirely hydrogen and helium. About 75% hydrogen, 25% helium by mass. Trace amounts of lithium. That's it. Those are the only elements that formed in the first few minutes after the Big Bang during the process called Big Bang nucleosynthesis. Everything else, every other element in the periodic table had to be created later, and stars are what created them. Inside stellar cores, as hydrogen fuses into helium, the core gradually becomes richer in helium and hotter. Eventually, in stars massive enough, the helium itself begins to fuse. Helium fuses into carbon and oxygen. Then, in even more massive stars, those elements fuse into heavier ones. Carbon into neon and magnesium. Oxygen into silicon and sulfur. Silicon into iron. This process of nucleosynthesis builds up the periodic table step by step, creating elements that didn't exist when the universe began. And when massive stars die in supernova explosions, They scatter these newly created elements into space. They enrich the interstellar medium with heavy elements: carbon, oxygen, nitrogen, iron, all the elements necessary for planets and life. The Sun is a third-generation star, maybe fourth. It formed from a cloud of gas that had been enriched by previous generations of stars. That's why Earth exists, why rocky planets exist in our solar system, why we have the chemistry necessary for life. Because earlier generations of stars created the elements and scattered them into space through supernovae. This process, this stellar alchemy, it's been going on for most of cosmic history. For about 13 billion years, stars have been creating elements and distributing them throughout the universe, gradually enriching the cosmos with the raw materials for complexity. And we're living during a time when this process has had enough time to produce an abundance of heavy elements. The universe is now about 2% heavy elements by mass. That might not sound like much, but it's 2% more than it started with, and that 2% makes all the difference. It's what allows rocky planets to form, what allows complex chemistry to occur, what makes life possible. But this abundance of heavy elements, it's a product of time. It required billions of years of stellar processing, multiple generations of stars living and dying and enriching the interstellar medium. The early universe didn't have this. The first stars formed from nearly pure hydrogen and helium. They couldn't have rocky planets, couldn't have had the chemical complexity we have now, and in the far future, star formation will have ceased. No more stars will be creating elements. The existing stars will burn out, taking their fusion reactors offline. The process of nucleosynthesis will stop. The universe will have whatever heavy element abundance it has at that point, and it won't increase anymore. We're living during the active phase, when stars are still forming, still fusing, still creating elements, when the universe's chemical richness is still increasing. That's another aspect of the golden era. We're here during the time when the universe is actively becoming more complex, when new chemistry is being created, when possibilities are expanding rather than contracting. Now, let me talk about something that might seem contradictory at first. I mentioned earlier that star formation peaked about 10 billion years ago and has been declining since. We're making fewer new stars each year than we did billions of years ago. So, how can I say we're in a golden era if star formation is declining? Isn't that evidence that the golden age is already past? Not quite. Because what matters isn't just the rate of star formation, it's the combination of factors: the total number of stars, the abundance of heavy elements, the stability of conditions, the observability of the universe. Yes, we're past the peak of star formation, but we're not past the peak of habitability, not past the peak of chemical complexity, not past the peak of observational opportunity. Let me explain what I mean by walking through the star formation history in more detail. In the early universe, the first few 100 million years, there were no stars, just darkness. Then the first stars formed. Population 3 stars, massive and short-lived. They died quickly, enriching the interstellar medium with the first heavy elements. Then came population 2 stars, formed from slightly enriched gas. Still not many heavy elements, but more than before. These stars were smaller on average, longer lived. Many are still around today. The oldest stars in our galaxy are population 2 stars formed in the first billion years or so. Then came population 1 stars, like the Sun, formed from gas enriched by multiple previous generations. These stars have much higher heavy element content. They're the ones most likely to host rocky planets with complex chemistry. Star formation ramped up over the first few billion years of cosmic history. More and more gas collapsed into stars. More and more galaxies formed and began actively producing stellar populations. The rate peaked around 3 to 4 billion years after the Big Bang, about 10 billion years ago. At that time, the universe was forming stars at a rate about 10 times higher than today. But here's what's important. At that peak, conditions were less stable. Galaxies were colliding more frequently. Supernovae were more common. The radiation environment was harsher. And, crucially, even though star formation was higher, the total mass of heavy elements was lower than it is now. The universe was younger. Fewer generations of stars had lived and died. Less nucleosynthesis had occurred. The chemistry was less rich. Since that peak, star formation has declined, but the total amount of heavy elements has continued to increase. Every star that dies, especially every massive star that goes supernova, adds to the cosmic abundance of elements. So, even though we're making fewer new stars, the stars we're making now, and the planets that form around them, have access to richer chemistry than at any previous time. Think about it like compound interest. The early universe was investing heavily in stars, forming them at a high rate. But the total accumulated wealth of heavy elements was still relatively low. Now the investment rate has decreased. We're forming fewer new stars each year, but the total accumulated wealth is higher than ever, and it will keep increasing for trillions of years as existing stars continue to die and enrich the interstellar medium. We're living after enough time has passed to accumulate significant heavy element abundance, but before star formation has completely ceased. We're in the mature phase, where the benefits of billions of years of stellar processing are available, but the universe is still active enough to be interesting. That's the sweet spot. That's why this is golden, even though we're past the peak of star formation. Because what we care about isn't just quantity, it's the right combination of factors, and that combination exists now in ways it didn't exist at the peak and won't exist in the far future. Consider life. Complex life, life like us. We require specific conditions. A stable star that burns steadily for billions of years. The Sun is perfect for this. It's been burning hydrogen at a stable rate for 4.6 billion years. It will continue for another 5 billion years or so before beginning to evolve into a red giant. That's a long stretch of stability, long enough for planets to form, cool, develop atmospheres, allow chemistry to become complex, and for life to emerge and evolve. But we also require heavy elements. Carbon-based life, which is the only kind we know about, needs carbon, needs oxygen, needs nitrogen and phosphorus and various other elements. all of which had to be created in stars. The early universe couldn't host life like us because those elements weren't abundant yet. Even if stable stars existed, even if planets formed, the chemistry wouldn't have been there. The building blocks wouldn't have been available. There's a concept called the habitable epoch of the universe, a window of time when conditions are most favorable for life. Too early, and there aren't enough heavy elements. Too late, and star formation has declined to the point where new opportunities are rare. Where in that habitable epoch, we exist during a time when the universe has had enough time to create the chemistry we need, but hasn't aged so much that opportunities are scarce. And this timing isn't arbitrary. It's a consequence of how long it takes for stellar processing to enrich the universe, and how long stars like the sun live. Life that emerges around sun-like stars requires billions of years of stellar evolution to have occurred first to create the necessary elements, and it requires the star to remain stable for billions of years to allow biological evolution to proceed. These timescales naturally put complex life in the mature phase of the stelliferous era. Billions of years after the Big Bang, when multiple generations of stars have lived and died, but long before star formation ceases entirely. So, again, the timing isn't coincidence, it's necessity. Complex life requires these conditions, and these conditions exist during what we'd call the Golden Era. For other reasons too. The universe is observable, structure is developed, stars are abundant. All the things that make this time special also happen to be the things required for complex life to exist. It's all connected. The universe is a package deal. The conditions that allow us to exist are the same conditions that make this a remarkable time cosmically. Now, let me paint you a picture of what the far future looks like, because to really appreciate the Golden Era, you need to understand what comes after, what the universe will be like when the age of starlight ends. Fast forward trillions of years, the stelliferous era is ending. The last massive stars have already died. No more supernovae. The last medium-sized stars like the sun have evolved into red giants and then shed their outer layers, leaving behind white dwarfs. What remains are the smallest stars, red dwarfs, stars with masses around 10 to 20% of the sun. These miserly little stars burn their hydrogen so slowly that they can last for trillions of years. 10 trillion years or more for the smallest ones. They're the last lights in the universe, the last stars still fusing hydrogen, and, for a while, for trillions of years, they keep the universe from being completely dark. But they're dim. Each red dwarf produces a tiny fraction of the sun's light, and they're the only stars left. Galaxies that once contained billions of bright stars now contain only these dim embers. The night sky, from any planet still capable of hosting observers, is much darker than what we see now. Fewer stars, dimmer stars, a fading cosmos. And then, one by one, even the red dwarfs run out of fuel. The smallest and longest-lived ones last the longest. But around 10 trillion years after the Big Bang, about 10.2 trillion years from now, the last red dwarf exhausts its hydrogen. The fusion stops. The star contracts and cools, becoming a white dwarf. And, with that, the stelliferous era ends. No more stars are fusing hydrogen. the age of starlight is over. What replaces it? The degenerate era, an age dominated by stellar remnants, white dwarfs cooling slowly in the darkness, neutron stars spinning down, black holes lurking silently, brown dwarfs, objects that never quite had enough mass to ignite fusion, now just cold balls of hydrogen. This is a dark universe, a quiet universe, a universe that's fundamentally different from what we know. There are no more stellar nurseries, no clouds of gas collapsing to form new stars. All the available gas has either been locked up in existing stellar remnants or blown out of galaxies, or so diffused by the expansion of space that it will never collapse again. The universe has used up its fuel, and without fusion, without stars, the primary energy source that's powered the cosmos for trillions of years is gone. Now, white dwarfs are still warm. They're not fusing anything, but they have thermal energy. When a star like the Sun becomes a white dwarf, it starts out incredibly hot, over 100,000 Kelvin at the surface. That's hotter than the Sun's surface now, and it glows brightly, relatively speaking. But white dwarfs have no energy source. They're just cooling embers, hot objects radiating their heat into the surrounding space. And because they're so dense, because they have about half the mass of the Sun compressed into a volume the size of Earth, they cool very slowly. It takes billions of years for a white dwarf to cool significantly. But cool they do, slowly but inexorably. After 100 billion years, a typical white dwarf might have cooled to a few thousand Kelvin, still glowing red. After 1 trillion years, maybe 1,000 Kelvin or less. Infrared, invisible to the eye but still radiating. After 10 trillion years, a few hundred Kelvin, cold by any standard, but still warmer than the cosmic background. And the cooling continues for timescales that dwarf even the stelliferous era. Quadrillions of years, quintillions. The white dwarfs gradually approach the temperature of the cosmic microwave background, which itself is cooling as the universe expands. Eventually, after about 10 to the power of 20 years, give or take, the white dwarfs have cooled to the temperature of their surroundings. They're black dwarfs now, cold, dark spheres of carbon and oxygen, no longer emitting any detectable radiation, invisible except for their gravitational influence. This is the far future. The universe of black dwarfs and neutron stars and black holes, of objects that no longer produce energy, that are just slowly cooling or slowly evaporating or slowly spiraling toward gravitational interactions. It's nothing like the universe we know, nothing like the golden era. Any civilization existing in that time, if civilizations can still exist without stars, will live in profound darkness. They won't see a sky full of stars, won't observe galaxies, won't watch star formation or supernovae, or any of the dynamic processes that characterize our time. They'll have a cold, dark, nearly empty universe, and they'll know, from whatever records survive, that it wasn't always this way. That there was a time, trillions of years earlier, when the universe was full of light, when stars filled space and galaxies shone brilliantly and the cosmos was vibrant and active. They'll know about the golden era, but they won't be able to experience it, won't be able to see what we can see. And they'll envy us. They'll look at our observations, our photographs, our catalogues of billions of galaxies and trillions of stars, and they'll wish they could have been here. Wish they could have seen the universe during its age of starlight. That's what's coming. That's the future. And it makes our present all the more precious, all the more remarkable. We're here during the light, before the darkness. We're witnessing something that won't last, and that makes it golden. But there's more. Even the degenerate era doesn't last forever. Fast forward even further, beyond trillions of years, into timescales measured in 10 to the power of 30 or 40 or 50 years. Numbers so large they're almost meaningless, but we can describe what happens. Protons, the positively charged particles in atomic nuclei, might not be stable forever. Some theories predict they decay very slowly on timescales of 10 to the 34th years or more. If protons decay, then even the black dwarfs and neutron stars won't last. They're made of protons and neutrons. If those decay, the stellar remnants gradually disintegrate. This is speculative. We've never observed proton decay, but it's predicted by some theoretical frameworks. And if it happens, it means that eventually even the stellar remnants from the stelliferous era will be gone, dissolved, decayed into lighter particles and radiation. What remains are black holes, and black holes, remarkably, also evaporate. Not through proton decay, but through a quantum mechanical process discovered by Stephen Hawking. Black holes emit radiation called Hawking radiation due to quantum effects near the event horizon. This radiation is incredibly faint for large black holes, but it's real, and it means black holes slowly lose mass. Very slowly. A black hole with the mass of the Sun would take about 10 to the 67th years to evaporate completely. A supermassive black hole with 1 billion solar masses would take about 10 to the 100th years. These are timescales so long that they make the age of the universe seem like a brief moment. But eventually, even black holes evaporate. And when the last black hole finally evaporates, emitting its final burst of Hawking radiation, the black hole era ends. What's left? The dark era, a universe that has reached maximum entropy, a thin soup of particles spread across an incomprehensibly vast and cold space. Photons with wavelengths stretched to enormous lengths by the expansion of the universe. Neutrinos, maybe some exotic particles, all at temperatures infinitesimally close to absolute zero, no structure, no complexity, no energy gradients to drive processes, just a cold, dark, nearly uniform soup approaching thermodynamic equilibrium. This is heat death, the final state of the universe according to our current understanding, a state where nothing can happen anymore because there's no free energy to drive change. The universe has run down like a clock that's wound down. It still exists. Space and time continue, but nothing interesting happens. Nothing changes. It's the end. Not a dramatic explosion, but a slow fade into darkness and silence and cold. This is where the universe is headed. This is what comes after the golden era, after the age of starlight, after the brief, cosmically speaking period when stars filled the cosmos and made it interesting. That final state, that heat death, it's not billions or trillions of years away. It's 10 to the 100 years away or more, a timescale so enormous that it's hard to even conceptualize. But it's coming. The universe is evolving toward it, slowly, inexorably, and once it reaches that state, it might stay there forever. Maximum entropy, equilibrium, the end of cosmic evolution. When you understand this trajectory, when you see where the universe is going, it makes the present moment stand out. We're so far from heat death, so far from maximum entropy. We're living during a time of low entropy, high complexity, abundant structure and energy. The universe is full of gradients, hot stars and cold space, dense galaxies and empty voids, structure on every scale. And these gradients, these departures from equilibrium, they're what make things happen. They're what allow processes to occur, stars to shine, planets to orbit, life to exist, chemistry to be interesting. But entropy always increases, gradients always smooth out, and eventually, far in the future, the universe will have no more gradients, no more structure, no more complexity, just uniform, maximum entropy equilibrium. We're witnessing the universe during its structured phase, its complex phase, its interesting phase, before the long slide into equilibrium. And that makes now special, makes this era golden, because complexity won't last, structure won't persist. The universe is on a one-way journey from low entropy to high entropy, from ordered to disordered, from complex to simple. And we're alive during the complex part, the ordered part, the interesting part. That's a gift, a temporary, cosmically speaking gift. But we're here to receive it. Let me bring this back to something you can relate to, something immediate and personal. You are made of atoms, carbon, oxygen, hydrogen, nitrogen, phosphorus, and traces of other elements. Those atoms weren't always part of you. They've had a long history. The hydrogen in your body, that's primordial. It formed in the first few minutes after the Big Bang during Big Bang nucleosynthesis. That hydrogen is about 13.8 billion years old. It's been around since the beginning, but the heavier elements, the carbon and oxygen and everything else, those were created in stars, forged in stellar cores through fusion. Some of those atoms were created in stars that lived and died billions of years ago. Some might have been created more recently, cosmically speaking, but all of them came from stars. When massive stars died in supernova explosions, they scattered their fusion products into space. Those atoms mixed with the interstellar medium. Eventually, they became part of a molecular cloud. That cloud collapsed to form the sun and the solar system. Some of those atoms ended up in Earth, in the oceans, in the atmosphere, in the rocks, and eventually, through the chemistry of life, some of those atoms ended up in you. You are literally made of stardust, the fusion products of long-dead stars, and the fact that you exist, that those atoms arranged themselves into something as complex as a living, conscious being. That's only possible because we're living in the right era. The universe has had enough time to create the heavy elements, enough time for stellar processing to enrich the cosmos with the chemistry of life. But not so much time that opportunities have passed. Star formation is still happening. Stars are still creating new chemistry. The universe is still actively enriching itself. You're a product of this golden era. Your existence is tied to the timing, too early, and the necessary elements wouldn't have been abundant enough. Too late, and the conditions for new life might be less favorable as star formation declines and the universe continues to expand and cool. You're here now because now is when complex chemistry is most abundant, when stable stars are common, when planets can form around them, when billions of years of stellar evolution have created the conditions for beings like you to emerge. And once you exist, once you're conscious and aware, you can look around, look up at the stars, understand where you came from, understand that the atoms in your body were forged in stellar cores, that you're connected to the cosmos in the most literal way possible. That understanding, that cosmic perspective, it's one of the privileges of living in the golden era. Not just that we can observe the universe, but that we can understand our connection to it, can see how we fit into the cosmic story, can appreciate that we're part of something vast and ancient and extraordinary. The stars aren't just distant lights. They're our ancestors in a sense, the furnaces that created the elements we're made of. And they're still shining, still visible, still creating new chemistry. We're living during their time, during the age when they dominate the cosmos. And that makes us, in a very real sense, children of the stars, products of the stelliferous era, beings whose existence is intrinsically tied to the golden age of starlight. You carry that heritage in every atom of your body, and you're alive to appreciate it, to understand it, to look up at the night sky and know that you're seeing your origins. That's profound, that's meaningful, that's part of what makes this era golden. Not just the physical conditions, but the fact that those conditions have produced beings capable of understanding them. The universe has become conscious of itself through us, has developed the ability to observe and appreciate its own structure and history, and that self-awareness, that cosmic consciousness, it exists during the golden era. During the time when the universe is most observable and most interesting. That's not coincidence. That's the result of billions of years of cosmic evolution. From hydrogen and helium to stars to heavy elements to planets to chemistry to life to consciousness. It's all connected. It's all part of the same story. The story of the universe becoming aware of itself. And that story is happening now, during your lifetime, during the golden age. You're part of it. You're witnessing it. You're living it. And hopefully, after everything we've explored, you understand why that's so extraordinary, why the timing matters, why this moment in cosmic history is so special. The universe is 13.8 billion years old. It will exist for timescales measured in tens or hundreds of trillions of years, perhaps far longer. And you exist during the brief window when stars fill the cosmos with light, when galaxies are visible across vast distances, when the cosmic microwave background still reveals the universe's beginning, when chemistry is rich and complex, when life is possible and consciousness has emerged. That's the golden era, and you're living in it, right now, at this very moment. As you listen to these words, as you contemplate your place in the cosmic story, you're here during the universe's prime, during the age of starlight, during the time that future civilizations, if they exist, will look back on with envy and wonder, because we have what they'll have lost, light, structure, observability, the privilege of witnessing the universe during its most magnificent phase. That's your cosmic inheritance, your birthright as a conscious being in the stelliferous era. And understanding that, really grasping what it means to live during the golden age, it should change how you see everything, should make you appreciate the stars, should make you value the privilege of consciousness, should make you realize that we're witnessing something precious and temporary. The age of starlight won't last forever. The golden era will end. The universe will continue evolving toward darkness and silence and maximum entropy. But that's trillions of years in the future. Right now, in this moment, the stars are shining, the galaxies are visible, the universe is revealing its secrets, and we're here to see it all, to appreciate it, to understand it, to preserve what we learn for whatever comes after. That's our privilege, our responsibility, our gift from the cosmos. We're the witnesses to the golden age. And what we do with that privilege, how we use this moment, that's up to us. Thank you for taking this journey through cosmic time with me, for understanding why our moment is so special, for appreciating the golden era while we're living it. If this changed how you see the universe, if it made you appreciate the stars in a new way, please consider subscribing to this channel. Share this with someone who might find it meaningful. Help spread the understanding that we're living during an extraordinary time in cosmic history. And tonight, go outside, look up at the stars, see them with new eyes, with the knowledge of what they represent, with the understanding of when you exist in cosmic time, with the appreciation that you're witnessing the golden age of starlight. The universe is beautiful, it's vast, it's ancient, and it's shining its brightest during your watch. Don't take that for granted. Appreciate it, marvel at it, understand how fortunate you are to be here during this cosmic moment. The stars won't shine forever, but they're shining now, and you're here to see them. That's the golden era. That's your inheritance. That's the gift of existing in the age of starlight. Make the most of it. Look up, wonder, appreciate, and remember that you're part of something extraordinary, something that won't last forever, but that's happening now, during your time, during the universe's golden age. Good night. And may you always remember that you're living during the most remarkable moment in cosmic history. Let me help you understand even more deeply what we're observing that future civilizations won't be able to see. Because this isn't just abstract theory. This is about real observations we're making right now that are only possible during our cosmic moment. Consider the cosmic microwave background in more detail. When we observe it with satellites like Planck, we're not just seeing uniform radiation, we're seeing patterns, fluctuations in temperature across the sky. These fluctuations are tiny, about 1 part in 100,000. Regions that are slightly warmer or slightly cooler than the average. But these tiny variations, they're incredibly important. They tell us about the distribution of matter in the early universe, about the density of different regions, about where galaxies would eventually form. The pattern of these fluctuations depends on fundamental physics, on the density of ordinary matter, on the density of dark matter, on the properties of dark energy, on how sound waves propagated through the early universe plasma. By measuring the pattern precisely, we can determine all of these fundamental parameters. We can figure out what the universe is made of, how old it is, how fast it's expanding, what its geometry is, all from studying the cosmic microwave background. This is extraordinary. We're learning about the universe as it was just 380,000 years after the Big Bang. We're seeing the seeds of all future structure. We're measuring fundamental cosmological parameters with precision. And we can do this because the cosmic microwave background is still bright enough to observe, still warm enough that its fluctuations stand out above the background noise. But, as I mentioned, it's cooling. As the universe expands, the wavelength of this radiation stretches, the temperature drops, and the signal becomes weaker relative to other sources of noise. In another 100 billion years, the cosmic microwave background will be 10 times colder, about 0.3 Kelvin. The fluctuations will still exist, but they'll be 10 times smaller in absolute terms. And the relative contribution from other sources of radiation will be larger. It will be harder to extract the signal, harder to measure the fluctuations precisely, harder to determine cosmological parameters. In 1 trillion years, it will be essentially impossible. The cosmic microwave background will have cooled to the point where it's buried in noise, where the signal is so weak that no realistic detector could measure it accurately, and beyond that, it keeps cooling, eventually becoming completely undetectable. Future civilizations, living trillions of years from now, will not be able to observe the cosmic microwave background. They won't be able to measure its temperature, won't be able to map its fluctuations, won't be able to extract the cosmological parameters we've measured. They'll have lost this window into the early universe, this direct evidence of the Big Bang, this tool for measuring fundamental physics. Now, they won't be completely ignorant. They'll have other evidence for the Big Bang. The expansion of the universe will still be observable. The abundances of light elements, hydrogen and helium and lithium, those will still reflect Big Bang nucleosynthesis. They'll have theoretical models, but they won't have the cosmic microwave background, won't have that direct snapshot of the universe at 380,000 years. That's a loss. A real loss of observational capability. And it's something we have that they won't. We can see the cosmic microwave background. We can measure it. We can learn from it. And that's a privilege of our cosmic moment, a feature of the golden era. The evidence is still there, still accessible, still revealing the universe's secrets. And we're taking advantage of it, mapping the sky, measuring the fluctuations, extracting the parameters, creating detailed maps that will be preserved for future generations, future civilizations, future eras when direct observation is no longer possible. That preservation, that documentation, it's important. It's part of our cosmic responsibility. We're the ones who can see these things. We're the witnesses. And what we observe and record will be the only evidence future eras have that these phenomena ever existed at this level of detail. Consider another example, the large-scale structure of the universe, the cosmic web. I mentioned this earlier, but let me go deeper. Right now, we can observe galaxies across billions of light years. We can measure their positions, their distances, their velocities. And when we map them in three-dimensional space, we see structure. Galaxies aren't randomly distributed. They cluster together in groups and clusters. These clusters connect to each other via filaments. Long, thin structures containing galaxies and dark matter. Between the filaments are voids, vast empty regions with few galaxies. The overall pattern looks like a web, like a cosmic spider web with galaxies along the threads and empty space in the gaps. This structure, this cosmic web, it's the result of gravitational evolution. Small density fluctuations in the early universe, the same fluctuations we see in the cosmic microwave background, grew over time. Denser regions attracted more matter, became denser, collapsed into galaxies and clusters. The pattern we see reflects the initial conditions, reflects how structure grows through gravity, reflects the role of dark matter in shaping the distribution. By studying the cosmic web, we're learning about fundamental physics, about the nature of dark matter, about how gravity works on cosmological scales, about the initial conditions of the universe. But mapping the cosmic web requires observing many galaxies across large volumes. And that's only possible because those galaxies are still visible, still close enough that their light reaches us. The accelerating expansion is carrying distant galaxies away from us, and not just away, but accelerating. The recession velocity increases over time. Eventually, galaxies will recede so fast that their light can never catch up to us. They'll cross the cosmic horizon. They'll become unobservable. This is already happening to the most distant galaxies. The most distant objects we can see are receding from us faster than light. Not because they're moving through space faster than light, which would violate relativity, but because the space between us and them is expanding so fast that the effective recession velocity exceeds the speed of light. We can still see these objects because the light was emitted when they were closer, when the recession velocity was less than light speed. That light has been traveling toward us ever since, fighting against the expansion of space. And eventually, it reaches us. But there's a limit. Objects beyond a certain distance will never be visible to us. Their light will never reach us because the expansion of space between us and them is too fast. The horizon is at about 46 billion light years, which is the edge of the observable universe. But that horizon, that boundary, it's not fixed. As the universe continues to expand and accelerate, more and more galaxies will cross that boundary, will recede beyond observability. In about 150 billion years, all galaxies outside our local group will have crossed the horizon. They'll be gone, invisible. No amount of telescope power will bring them back. Future astronomers living in the Milky Way, or more likely in the merged Milky Way Andromeda galaxy called Milkomeda, will look out and see only their local group, maybe a few dozen galaxies. That's it. They won't see the cosmic web, won't see the filaments and clusters and voids, won't be able to map large-scale structure, because the evidence will have expanded beyond their reach. They'll have our maps, our catalogs, our measurements, but they won't be able to extend them. won't be able to discover new aspects of large-scale structure, won't be able to verify our observations independently. That's another loss, another reduction in observational capability, another aspect of the universe that's visible now but won't be visible forever. We're catching the cosmic web while it's still observable, documenting it, creating maps, measuring properties, and those maps, those observations, they'll be valuable to future civilizations. They'll be the only record of what large-scale structure looked like during the era when it was still observable. That's what I mean by the Golden Age. We have observational access. We can see things that won't always be visible, and we're using that access to learn and document and preserve. Then there's star formation itself. I've mentioned that star formation is declining, that we're past the peak, but let me help you appreciate what we're still able to observe that future eras won't see. Star formation happens in molecular clouds, dense regions of gas and dust where gravity pulls material together until it becomes dense and hot enough to ignite fusion. We can observe these stellar nurseries, places like the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword. Through telescopes, we can see detailed structure, clouds of gas glowing from the radiation of newly formed stars, dark lanes where dust blocks light, protostars embedded in the clouds, not yet hot enough to start fusion, but already accumulating mass. This is star formation in action, the process of creating new suns. And we can watch it happen, not in real time, because the timescales are millions of years, but we can see stars at different stages. Protostars just forming, young stars recently ignited, slightly older stars that have cleared away their surrounding gas. By observing many examples at different stages, we can piece together the sequence, can understand how stars form, can see the process directly. But in the far future, when star formation has ceased, this won't be possible. When all the gas has been consumed or dispersed or locked up in existing stars, there will be no more stellar nurseries, no more protostars, no more recently ignited young stars. Astronomers in that era will understand stellar physics, will know how fusion works, will be able to calculate theoretically how stars should form, but they won't be able to observe it directly, won't be able to see stellar nurseries in action. That's another privilege of our era. We're witnessing active creation. The universe is still making new stars. And we can watch the process, can study it, can learn from direct observation rather than just theory. That won't always be possible. That's temporary. A feature of living during the stelliferous era while star formation is still ongoing. And we're taking advantage of it, observing stellar nurseries, studying protostars, watching young stars interact with their surroundings, creating detailed understanding of how star formation works. Understanding that will be preserved and passed down to future eras when direct observation is no longer possible. Consider supernovae as well. These spectacular explosions happen when massive stars reach the end of their lives. The core collapses into a neutron star or black hole. The outer layers are blown off in an explosion that releases more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. We observe supernovae regularly, several per year in nearby galaxies if we monitor them carefully, many more in distant galaxies. Each one is an opportunity to study stellar death, to understand the physics of core collapse, to measure how heavy elements are created and distributed, to use the explosion as a distance indicator to measure cosmic expansion. But supernovae require massive stars, and massive stars require active star formation because they don't live very long. A star 20 times the mass of the Sun lives for only about 10 million years before going supernova. As star formation declines, as fewer massive stars are born, supernovae become rarer. Eventually, when star formation ceases entirely, when the last massive stars have already died, supernovae will stop. There will be no more core collapse supernovae. Future astronomers will study the remnants of ancient supernovae, will understand the physics from our observations and theories, but they won't see new ones happening, won't be able to observe the light curve, won't be able to measure the spectrum as the explosion evolves. That's another temporary phenomenon, another aspect of the universe that's active now but won't be active forever. And we're the ones who can observe it, who can study it, who can document it for future eras. All of these examples, the cosmic microwave background, the cosmic web, star formation, supernova, they illustrate the same point. We live during a time when the universe is observable, when it's revealing its processes, when evidence of its history and structure is accessible. That won't always be true. The universe is evolving, cooling, expanding, accelerating, and as it does, observational opportunities decline. Future civilizations will have less access, will see less, will have to rely more on theory and on preserved observations from earlier eras. We're living during the era of direct observation, the age when the evidence is abundant, when the universe is an open book. That's the golden age, and we're not wasting it. We're building telescopes, making observations, creating catalogs, documenting everything we can see, preserving that knowledge for the future. That's our gift to civilizations that will come after us, our contribution to the long-term project of understanding the universe. We're the witnesses, the observers, the documenters of the golden age. And that's a profound responsibility, a meaningful role, a purpose that connects us to the vast sweep of cosmic time. Now, let me talk about what this means for you personally, for how you should think about your life and your place in the universe, because this isn't just abstract cosmology. This is about perspective, about understanding where and when you exist. You are élevé during the golden age of Starlight, during a time that's cosmically brief but extraordinarily rich. The universe has arranged itself such that complex beings can emerge, become conscious, and observe the cosmos during its most spectacular phase. That's not random, that's not meaningless, that's profound. You're part of something vast, part of the universe's ongoing story, and you exist at a moment when that story is particularly interesting, when the main character, so to speak, is in its prime. That should give you perspective. should make your day-to-day concerns feel smaller when viewed against the backdrop of cosmic time, should make you appreciate the bigger picture, but it should also make you feel connected. Connected to the stars that created the atoms you're made of, connected to the long history of cosmic evolution that made your existence possible, connected to the vast future that stretches ahead. You're a node in the cosmic network, a point of consciousness in a universe that's mostly unconscious. And you exist during a time when consciousness has much to observe and appreciate. That's special, that's meaningful, and it comes with responsibility. Not legal or moral obligation, but cosmic responsibility. You have the capacity to understand, to appreciate, to wonder at the universe's majesty, and in doing so, you're fulfilling a role. You're being the universe's witness, its observer, its consciousness, the part that's aware of the whole. That's what makes being human during the Golden Age so extraordinary. We're not just living organisms struggling to survive and reproduce. We're conscious beings capable of cosmic perspective, capable of understanding our place in space and time, capable of appreciating the privileged moment we inhabit. Use that capacity. Look up at the stars regularly. Think about cosmic timescales. Consider your place in the universe's long story. Don't get so caught up in the immediate that you forget the vast context. Because that context, that cosmic perspective, it's available to you. It's one of the gifts of living during the Golden Age. You can observe the stars, can learn about the universe, can understand your origins and your place in the cosmic story. Not everyone throughout history has had that opportunity. Ancient humans looked up at the same stars, but didn't know what they were. Didn't know about the vast distances. Didn't know about cosmic time. Didn't have the scientific framework to understand what they were seeing. And future humans, if they exist trillions of years from now, will look up at a much darker sky, will see far fewer stars, will have less observational evidence about the universe's history and structure. But you, right now, you have the full experience. Stars filling the sky, scientific understanding of what they are and how they work, knowledge of cosmic history and your place in it, telescopes that can show you distant galaxies and stellar nurseries and supernova remnants. That's the complete package. That's the full Golden Age experience, and it's yours, right now, available to you if you choose to engage with it. Don't waste that opportunity. Don't live your entire life focused only on the immediate and the local. Take time to look up, to wonder, to appreciate that you're living during an extraordinary cosmic moment. The stars are shining, the universe is observable, and you're here to witness it. That's the privilege of existing during the Golden Age. That's your cosmic inheritance. Make the most of it. Appreciate it. Let it give you perspective and meaning and connection to something larger than yourself. Because this is your moment, your time, your cosmic era, and it's golden. The stars won't shine forever. The universe won't always be this observable. The Golden Age will pass. But it's happening now, during your watch, and you get to be part of it, to witness it, to appreciate it. That's extraordinary. That's meaningful. That's what makes living during the age of starlight so special. Thank you for exploring this with me, for understanding why our cosmic moment matters, for appreciating the golden age we're living in. If this resonated with you, please share it. Help others understand the privilege of existing now during the universe's most magnificent era. Look up tonight, see the stars, and remember that you're witnessing something precious and temporary, the golden age of starlight. And it's yours to experience, right here, right now. Make the most of it.